Welcome back to Calculus 2. Today we're going to continue our discussion of sequences and series. And we're going to talk about quite a bit of theory today, specifically dealing with limits and convergence / divergence of sequences. So, a little bit more theory heavy than usual. We'll have more examples in later videos. Here is the formal definition of sequence convergence, of the convergence of a sequence. It's very similar to the convergence of a function as x goes to infinity. It's pretty much the same exact idea. It's just rephrased for talking about sequences. So the sequence, a sub n, converges to the number L if for every epsilon greater than 0, there is an integer n, such that for all n greater than n, a sub n minus L is less than epsilon. So, for an arbitrary epsilon, L is the limit of the sequence if you can bound the difference between the sequence values and the limit if you go far enough in the sequence. So, for any tiny little epsilon, like 0.1, eventually you could get a high enough n that everything beyond that would be within 0.1 of a sub n, or whatever epsilon is. If you want 0.000003, then eventually, if the sequence converges, you could find an n large enough that the distance between a sub n and L would be less than epsilon for every n greater than that. So like if it was the 300th term that finally a sub n was within epsilon of L, then every term after that would be within that range. That's how convergence works. And if there isn't a number for which that's true, then a sub n diverges. And yeah, it's basically the same definition we've seen before. Here's the definition of diverges. If you're going to show something diverges to infinity, you need to show it's eventually just higher than any finite number. So that's what they're saying here. M is just some finite number. It could be very large. But eventually, if your indexes are high enough, you'll be over that number, whatever it is. So, like say, we were looking at something that does diverge. How about, say, just the sequence a sub n equal n? Let's make it 2n, right? That diverges as n goes to infinity, this goes to infinity. And you can tell that if you let m equal, say, 7,000, right? There is a capital N such that if little n is bigger than that, this will be bigger than 7,000. I believe it would be 3,500. Yeah. N equal 3,500. So, like, if I plug in 3,501, this would become 7,002, which is bigger than that. So yeah, it diverges because no matter what m I pick, and you could even be specific about what m it is. In this case, you could just show 2n is greater than m. Well, that means just n has to be m over 2. Put my capital in there. So yeah, if n is greater than m over 2, then if little n is greater than m over 2, then a sub n will be greater than m, which means it must diverge. So yeah, that's the definition. Let's talk about some of the limit laws. These are basically the same limit laws we had for functions. If you take the limit of a term-by-term sequence sum, it is going to equal the sum of the limits. If you take the subtraction of the term-by-term sequence, you're going to get the subtraction of the limits. Constant multiple, so if you take a sequence, every term times a constant, well, your limit is going to be k times the limit. Multiply term by term a sequence, you'll just get the multiplication of the limits, and division, you'll just get the division of the limits, assuming the bottom one isn't 0 and it's undefined. I'm going to go ahead and prove one of these. I'm only going to prove one of them, though, because they're very simple to prove. Everyone's basically done the same way. So let's prove, say, limit as x approaches infinity of a sub n plus b sub n equals a plus b. And we know our given is if limit x or n goes to infinity, not x, n goes to infinity of a sub n equals a, and limit n goes to infinity of b sub n equals b. That's our given information. So our proof, basically I'm just going to state the definition. If limit n goes to infinity of a sub n equals a, and limit n goes to infinity of b sub n equals b, then for any epsilon greater than 0, there are I will call them N1 and N2, such that if n is greater than n1, let's see, a sub n minus a is less than epsilon, and n is greater than, and if n is greater than n2, then a sub n or b sub n minus b is less than epsilon. I got both my differences here bounded by epsilon. I'm going to let capital N equal the maximum of N1 and N2. Then, if little n is bigger than n, we must have a sub n plus b sub n minus a plus b. This would be the limit statement using the definition, because if this is the limit of this, then this whole subtraction in absolute value has to be less than epsilon. Well, if we rearrange terms, this is a sub n minus a, and b sub n minus b. And then by the triangle inequality, which if you took Calc 1 with me, you may remember, the triangle inequality says this. It's in, I think it's proved in one of our appendices, but it says if you have the absolute value of a plus b, this is less than or equal to the absolute value of a plus the absolute value of b. Could be equal, but it's certainly less than or equal to. So that means I can split this up as a sub n minus a in absolute value plus b sub n minus b in absolute value. And then we know those strictly are less than epsilon and epsilon. So 2 epsilon. And honestly, that's the proof. But if we were going to do it formally, we'd want this to come out to be just epsilon instead of 2 epsilon. So the only change you make is, because it's arbitrary what they approach in terms of epsilon, you just change these things to be epsilon over 2. And then these both become epsilon over 2, epsilon over 2, epsilon over 2. And there you go. That's equal that, equal epsilon. So yeah. And limit n goes to infinity of a sub n plus b sub n equals a plus b. And you'd finish the proof at that point. This is actually the statement that a sub n plus b sub n minus a plus b is less than epsilon. That the absolute value of a sub n plus b sub n minus a plus b is less than epsilon is the formal statement of this. So I'm just restating. Now that we've actually done this, we've done all the work, just restating that we've actually found it. So now our proof's done. And if I was doing this for pretty much any other of those rules, the sum rule, the difference rule, the constant multiple rule, whatever, anything with both a sub n and b sub n is basically just going to follow this. The subtraction's pretty much identical. The times and division, you have to do some more algebra tricks kind of to split it up. But I mean, it's very similar. If you go back and look at the proofs we did in Chapter 2, this is basically the same thing. So I'm not going to represent all the proofs of them. I just wanted to do one of them. Kind of get you back in the mode of thinking about abstract mathematics. Another big theorem back when we were talking about a function is still very helpful here. The sandwich or squeeze theorem for sequences. So if we have sequences a sub n, b sub n, and c sub n, if b sub n is in the middle between a sub n and c sub n always, it doesn't have to always be that way, but eventually, after n gets to a certain number, this is always true, that the b sub n term is always between the two. Well then, if the two upper and lower bounds both have the same limit, then the one in the middle does as well. It's called the squeeze theorem because if you think about it in a function form, if you got two functions both approaching the same value here at a, and you got something in between, well, because it's sandwiched or squeezed in between, it has to approach the same limit because of this. And I don't think I'm actually going to present the proof for this just because it is identical. It's identical to the proof we did in Chapter 1. You have to take account of having large n instead of talking about delta, but I mean, it's very similar. Yeah, it really just takes advantage of a limit law. We're going to go ahead and prove this one. Not because we haven't necessarily seen it before, but because it kind of has a neat proof, so it's worth revisiting. But this one says if you have a continuous function and you plug your sequence of values into it, then the sequence of those function values will still converge to the function value of the limit. So if I plug all these a sub n's into the function and it's continuous, then its limit of all those function values will be f of L. If we want to show this one, I think I might be able to actually just fit it on this slide. We might as well. Proof. We need to show there is an n greater than 0 such that if little n is greater than n, then f of a sub n minus f of L is less than epsilon. Well, what does continuity tell us? The definition of continuity says for any number c, the limit as x approaches c of f of x equals f of c. F continuous implies that. Alright, and we know a sub n goes to L. Alright then. Well, we want this to be bounded. And I think we can make that happen. Because we just have to follow the chain. So we know f of a sub n minus any other value, really. F of is less than epsilon if a sub n minus L is less than delta. But we can make that happen since a sub n converges to L. There is an n greater than 0 such that if little n is bigger than big N, a sub n minus L is less than delta. Alright, so just fixing up my proof here. We need to show that for any epsilon greater than 0, there is an n greater than 0, such that if n is greater than n, then this is true. For any c, we know that limit as x approaches c of f of x equals f of c. So as the inside approaches that, the function does as well. So we know this will be true if this gets close enough for some delta greater than 0. But we can actually make a sub n be as close to L as we want just by choosing n large enough. So if n is greater than n, a sub n minus L is less than delta, which implies f of a sub n minus L is less than epsilon, and we've proved our statement. We messed around a little bit. This proof's, if I were going to formally present this proof, I'd clean it up quite a bit in my language. It's basically just using the definitions. And our last theorem we're going to present is a theorem that allows us to use Lhopitals Rule. So this says if you have a function defined for all x greater than n naught, and honestly, it's just for some x greater than some index. And you have a sequence where a sub n equals f of n. So basically the formula for a sub n is the same as the formula for f. I might have my function equals 1 over x squared plus 1, and then my sequence might be basically the same formula, 1 over n squared plus 1. This is actually always equal for all of the integers, but you might define some function that only matches up to this formula after a certain sequence. I mean, it wouldn't be too hard to do. You could have, say, a piecewise function that for x less than 10 is 0, and then for x greater than or equal to 10 would be 1 over x squared plus 1. This would be for indices greater than 10. This formula would equal this sequence. For other ones, not so much. But yeah. So that's what we're going to do. We're going to show that if the limit as x goes to infinity of the function is L, then the limit as n goes to infinity of the sequence also has to be L. This is, much fewer values, so it makes a certain amount of sense if the function value for all real numbers goes to L as x goes to infinity. I mean, this is still going to infinity, it's just including a lot less terms. But still, it's going to infinity, so you expect the sequence to still go there, and it does. The proof is very simple. If n is greater than n naught, we know f of n equals a sub n, We also know for any epsilon greater than 0, there is an m such that if x is greater than m, then f of x minus L is less than epsilon. Let's choose n equals the maximum of m and n sub 0. Then, if little n is bigger than n, then a sub n minus L has to be equal to f of n minus L, which we know for any n value, for any x value, which the n's would be included, then that's less than epsilon, which is our proof. That shows a sub n has to converge to L. That'll finish us off on this video. When we come back, we will look at some examples, look at some different limits. We have a couple more definitions and theorems to get through, but we've got through most of it at this point. So, when we come back, we will look at some limits. Have a great day. See you in the next video.